Let's talk about what at first might seem like a difficult problem, but it's really not all that hard when you break it down into its pieces. Um, we have here a person that's simply walking along and carrying a bag. And this problem and the next problem are going to be related. So they're standing on the foot opposite to the bag. And we know that the bag is a fraction alpha of their weight. In your problem online, it'll give you an actual number. We know that the bag distance from the midline on the person to the bag is some distance x bag. They're standing on the opposite leg. You take the distance from the midline um, to what I'm going edge of the hip. From here, the midline to the hip is x mid meters, and the distance from the pivot point on the acetabulum, which is right here in this kind of diagram. We'll connect these two in a second to the outer edge of the hip is X hip, all right? So let's connect these. Here's the bag over here. Here's the midline on the person and their weight, which acts on the midline, and here's their foot on the ground, and the normal force exerting upwards on the foot. And this is the force of the muscle on the greater on the greater trochanter, and this is the net force from the acetabulum on the head of the femur, right? These are internal forces. We're not worried about those just yet. Because the first thing we have to do, this is clearly a statics problem, right? And so the first thing we have to do is we have to start looking at the external forces, which are the normal force on the bottom of the foot, the gravitational weight of the person, W, and the weight of the bag, all right? So let's move on to the next bit and start looking at that, right? So the sum of the forces have to be zero, and the sum of the torques have to be zero. Again, for right now, we're ignoring these two forces. They're internal forces, and they're there simply because I have to use them in a little bit. And I have to add to this diagram. So if we look at this and we say, okay, so the sum of the forces has to be zero. Well, let's take up to be positive, down to be negative, and so that means N minus W minus W bag is zero, right? And in fact, we know W bag is this alpha times W, the weight, your weight, because we expressed it in terms of a fraction of the weight. The reason we do this, because then we don't have to know how much the person weighs. It all works out. All right, so that tells us that the normal force has to be 1 plus alpha, right, times the weight of the person. Of course, right? That's how much the floor has to hold up. And if the floor is not holding up that much, you're falling through the floor. Or if the floor is pushing up on you harder than that, you're flying into the air. Um, okay, so we know that. We know that we now know the normal force as a function of the weight. And again, everything in this we're trying to get to as a multiplier on the weight, right? So the normal force is 1 plus alpha onto the weight. So now we have to look at the torques, right? Let's look at the torques. And so if we look at the torques, let's say around the midline, right? Torque is again force times distance, and we only need the perpendicular force. So if we look at the torque around the midline, then the W here doesn't contribute at all. It's just the normal force and the weight of the bag. All right, so consider the weight of the bag. What is it going to do? Well, the weight of the bag is going to make the person rotate, right, this way. That's what the weight of the bag is going to do. And the way I've drawn it here, the normal force is also going to make the person rotate that way. And so if you were actually standing as I've drawn here, you fall over. Not really what we want. So what does that mean? I've drawn this wrong, right? I need to take this distance x and put it over here so that we can now figure out what that distance is. All right? So we now know our normal force has to be The foot basically has to be between your center of mass and where the bag is, otherwise you fall over. All right, so what are the torques due to this? Well, if we look at the torques due to this, the positive torques, if you remember, are always counterclockwise. All right, so the positive torque is going to be the x times the normal force, and the negative torque is going to be x bag times the weight of the bag, which I'm going to go ahead and put as alpha W. And that has to add, well, I'll put weight bag. And that has to be equal to 0. All right. All right, so we can actually put in, this is x onto 1 plus alpha times the weight minus x bag onto alpha times the weight, and that equals 0. And you can already see here, we don't have to know what your weight is to figure out where you are. I mean, where x is, right? The only unknown in this, we know x bag, that's given. We know alpha, that's given. We don't know w, but it doesn't matter because it factors out here and divides out. And so we've got x, the quantity we're after. Where do you have to put your foot equals alpha over 1 plus alpha onto x bag. All right, we solve that algebraically. We get x is alpha over 1 plus alpha onto x bag. And that tells us where your foot is. Okay, so let's move on to the next piece because we're after these forces up here, which are internal in our kind of macroscopic look that we've taken to figure out what the normal force is and where you have to put your foot. All right, and we're going to move on and look at the next piece. All right, the next piece, we have to look internally. Okay, so internally, we have different things going on. We have the normal force still, right? I mean, this is, we're now looking at just the leg, and we're looking at the external forces on just the leg. So we're going to introduce a new force that wasn't in the other diagram. We've got the normal force. We have 1/7 of your weight, which is about how much your leg is going to weigh. And we now know, we know X, right? We know N in terms of W. We know X mid, we know X hip. We're after, no, I missed the F. Let me copy the F over. We're after F so that we can get to R, right? So we're going to do the same thing. In this, statics are still a problem, are still what rule us here, right? The sum of the forces equals 0, and I really should write this as vectors, but the sum of the torques equals 0. That's still where we are. So let's look at vertical forces. All right, let's look at vertical forces. What are the vertical forces? Well, vertical, taking up to be positive, we have N, right? We have plus F Fy, which is going to be F onto the sine of 70 degrees, minus Ry minus 1/7 of your weight. And all of that has to be equal to 0. Let's look at horizontal. Horizontally, what do we have? All we have horizontally, because the normal force is straight up, your weight is straight down. All we have is to the right, we have F cosine of 70 degrees minus Rx has to be equal to 0. All right? So that's where our forces get us. What do we have in terms of unknowns? Well, we know N as a function of W. We don't know F, and we don't know Ry, and we don't know Rx. So we have two equations here and only and three unknowns. So that's not going to do us. So how do we get out of this? We turn to the torques. Again, positive torques, right? We're going to talk about rotation about this point right here, right? About the acetabulum and the ball on the head of the femur. And so positive torques are counterclockwise rotations. So the normal force will cause that. The weight is going to cause a clockwise rotation, and F is going to cause a clockwise rotation. So when we look at the torques, we have the normal force. Now, how far away is the normal force from the acetabulum? So there's the distance x. There is plus, all right, x mid minus x hip, right? That gets us there. How far away is this force? 1/7 the weight of the leg. Well, we're gonna just make the assumption that it's halfway between the normal force and the edge of the hip, right? So we're just gonna make the assumption that the weight of the leg is somewhat evenly distributed. Not quite true, but we're gonna make that assumption to simplify our lives here. And so with that assumption in place, that means this position over to here is 1/2 of x plus x mid. And the distance from here to there is 1/2 of x plus x mid minus x hip, right? And so this 1/7 W onto 1/2 of x plus x mid minus x hip. All right, and that gets us to the lever arm, or the distance between this force of action and that point. And that leaves us with just the force F. Now, Fx in this direction doesn't cause any rotation, right? That's directly into the pivot point, doesn't do anything at all in terms of making you rotate. It's only the y component. And the y component is F sine of 70 degrees, right? And the distance is x hip, and all of that has to add to 0, right? That's what we get out of the torques. All of that has to add to 0. So now look at this equation. We know N in terms of W. We know W, right? We know X, we know X mid, we know X hip. The only thing we don't know is F. And this equation from the torques gives us F, all right? Once we have F, what do? We're going to take F, we're going to go back up here. This equation is going to give us Rx, right? This equation is going to give us Ry, and we're just going to use, we're just going to figure out the magnitude of R, right? R is just going to be square root of Rx squared plus Ry squared. And that's going to give us the total force on the acetabulum right here, or the total force from the hip onto the head of the femur. And this is all going to be as a factor of the weight W, right? So if you have trouble thinking about that, you could just set W to 1 and you get what you need, right? but that's all going to be as a function of the weight W. And then once you have that, you get this, um, this bit. So good luck with this problem. I hope this helps you work your way through it.